We're going to be looking at another example of finding the equation of a derivative function for a particular simple polynomial function. So let's look again at our definition for finding a derivative function. F prime of x equals the limit as h goes to 0 of f of x plus h minus f of x over x plus h minus x. So what does that mean again? Well, we have 2 points. One point at x, whose y value is f of x, and another point at x plus h, whose y value is f of x plus h. As we slide those 2 points together, our average rate of change from the secant line turns into the instantaneous rate of change of the tangent line. So the slope we get from the secant line between these 2 points gets closer and closer to the tangent line at just the point x, f of x, which is what we're trying to accomplish. In order for x plus h to move closer to x, h has to get closer to 0, which is why we take the limit as h goes to 0. To use this definition for deriving a derivative function for any particular function, we just have to substitute x and x plus h into the actual function to get the function value. So let's look at the function that we're going to look at. We're going to look at the function f of x equals x cubed. So for the y value for x, the y value is just going to be x cubed. The y value for x plus h is just going to be x plus h cubed. So applying this limit definition, we're going to substitute x plus h cubed for f of x plus h and x cubed for f of x, so that we have the 2 y values that go with these 2 x values for this particular function. Once again, if we substituted 0 for h, we're going to get x cubed minus x cubed over x minus x, which is 0 over 0, which is what we always get. So let's go ahead and do some expanding. We know from the binomial theorem that x plus h cubed is x cubed plus 3x squared h plus 3xh squared plus h cubed. So this is a time when that binomial theorem really comes in handy. And then remember, we have to subtract off the other y value, which is x cubed. Then x plus h minus x in the denominator. Now if we substitute 0 any place there is an h, these 3 terms would all become 0, and this term would become 0, and we still have x cubed minus x cubed and x minus x. But we also notice there's a way we can simplify this. We notice that we have x cubed minus x cubed, and we have x minus x, so we can simplify this and basically eliminate any terms that don't have an x or don't have an h in them. So now we have 3x squared h plus 3xh squared plus h cubed. So I'm going to factor an h out of each of these 3 terms. And when I factor an h out, I get 3x squared plus 3xh plus h squared all over h. Now I can eliminate that troublesome factor that's causing the discontinuity, and I can substitute 0 in for h, and I get 3x squared plus 3x times 0 plus 0 squared. 3x squared plus 3x times 0 plus 0 squared. Notice again, we're not substituting 0 for x, but for h. So that simplifies to 3x squared. So that means the derivative function for y, or for f of x equals x cubed is f prime of x equals 3x squared. So let's look at that graphically and see what happens graphically. So I've graphed the cubic function f of x equals x cubed. The derivative function f prime of x equals 3x squared tells us the slope of the tangent line, or the derivative, or the instantaneous rate of change. All 3 of those things are synonymous for each value of x. So if I substitute any value for x in here, square it and multiply by 3, I'm going to have the slope at that x value. And I didn't use specific values like I did for x squared, but I just want to show you in general what we notice. The function 3x squared is actually a parabola with its vertex at the origin. Basically, it's a parabola that looks kind of like this. In the case, there's the parabola, 3x squared, kind of stretched up a little steeper than x squared, but basically like that. So what we notice here is these values, except for 0, 0, are all positive. That tells me that the slope, except for 0, 0, of the graph y equals x cubed is always positive, and we see that. So we see if we look at this section of the graph in the quadrant 1 right here, this section here, we see that x is positive, y is positive, and the slope is positive. That because if x is positive, x cubed is positive, and 3x squared is also positive, meaning the slope is positive. If we look at the section of the graph down in quadrant 3, we see that x is negative, y is negative, because if I put a negative value for x and I cube it, I get a negative value for y, but the slope is still positive. Okay, we have positive slope in both quadrants 1 and 3, because if I put a negative value for x in the derivative function and I square it and multiply by 3, I'm still going to get a positive number. At 0, the slope is 0 and the y value is 0, because 0 cubed is 0 and 3 times 0 squared is 0. So we have a horizontal tangent line right here only at the point 0, 0. But the tangent lines in quadrant 1 and quadrant 3 will all be slanted up with a positive slope. So let's look at one specific example that shows us that we're getting positive slopes in both quadrant 1 and quadrant 3. We know that the point 1, 1 is on the graph of f of x equals x cubed because 1 cubed is 1. And the point negative 1 is on that graph because negative 1 cubed is negative 1. So those are 2 points on the graph. Now let's use the derivative function f prime of x equals 3x squared to find the slopes of the tangent lines at both of those points. So if we do f prime of 1, we get 3 times 1 cubed, which is 3, or 1 squared, which is 3. If we do f prime of negative 1, we get 3 times negative 1 squared, which is also positive 3. So this tells us the slope of the tangent line at both x equal negative 1 and x equals 1 is 3. And we can see that those tangent lines are clearly parallel. Because the derivative function is always positive except at 0, we're always going to get positive values for the slope at any values of x except for 0. Now, even doing this for each function could be tedious, so let's see if we can observe a pattern here. We found the derivative function for f of x equals x squared. We found that the derivative function was 2x. We found the derivative function for f of x equals x cubed, and we found that the derivative function was 3x squared. What do you think the derivative function would be for the function x to the 4th? What do you think the derivative function would be for x to the n? If you figured that out, then you are well on your way to your first bit of calculus.